Okay, whoa, what happened here? That's not what I want. All right, so our first question is one of the wave behaviors at a boundary kind of questions. Okay, at any boundary, when a wave crosses a boundary or meets a boundary, okay, two things can happen. Some of the wave will be transmitted, go through, and some of the wave will be reflected. Okay, what are some properties of the wave that will change when it enters the new medium? For the reflected waves, the crests could become troughs if the situation is right, yes. But for that wave that goes through, yeah, depending on whether the medium it goes into is more dense or less dense, some properties of the wave are going to change. Now, the medium controls essentially two properties of the wave. What are those two properties? Wavelength. Velocity. And velocity. Yeah, because frequency can't change, right? That's the one that can't. That was my next question. Okay. So, when the wave enters a new medium, its speed is going to change. It's going to speed up or slow down. And if it speeds up or slows down, it's also got to get longer or shorter. Okay? If it speeds up, it's going to get longer. That's how frequency stays the same, right? If one goes up, the other goes up. Okay? If we're looking at this, okay, frequency has to stay the same. Okay, that's V divided by wavelength. If V goes up, wavelength has to go up by the same amount so that frequency stays the same according to that formula. Everybody all right with that? Okay. So this first one says, draw a sketch of a trough approaching a fixed end. So like that. Okay. So the trough is going this way. All right. Now do a sketch of the of what happens after it hits the fixed end. Okay. What's going to happen when it hits the fixed end?
Small trough will go through it, and a slightly smaller trough will reflect off.
If this was a boundary between two media, possibly. But this is a fixed end. This is infinitely dense. Nothing can go into it. So the only thing that will happen here is reflection. And it will be
the same.
It'll be the same?
Slightly smaller.
When we hit something more dense, the reflection is inverted, right? It's tricky. That's why we're going over it.
Wait, and it gets bigger, or you just boundary?
No, it's the same. Sorry, it's supposed to be the same amplitude. Yeah. Okay. Because none of the wave energy goes into the fixed end, it all gets reflected, right? I mean, some might be lost. It might be a little tiny bit smaller, not like I drew it, which was bigger. Okay. It can't obviously increase in amplitude in this situation. Okay. But we would get an inverted wave, in this case upright or a crest, going back. Anytime a wave travels to a more dense medium, the reflection will be inverted. Okay? That's something you have to know. Okay? There are probably 4 questions in the multiple choice section of the unit exam that deal with wave behavior at a boundary, reflected wave like characteristics being an important part of those. Okay, now this one has to do with interference that we talked about the day before yesterday. So, draw 3 sketches showing waves before, during, and after complete destructive interference. So if I'm going to draw destructive interference, the 2 waves I draw to start this have to be opposite. Okay, and we're going to pretend those are exactly the same. All right, so that's the before picture. What's the during picture look like? It's going to be flat. Yeah, they're going to completely cancel each other. The principle of linear superposition says add the amplitudes. Okay, we could do this, right, and draw a hashed mark to indicate where those waves are located, but the amplitude of the medium is 0 at that point. All right, when I draw the after picture, does the crest go on the left or the right?
Left.
Left. Okay? They travel through each other, okay, and are not affected by the interference. Okay? Everybody all right with that? Okay, so that's an interference question. All right. There's definitely a question like this, but possibly even a little more involved, in the multiple choice section of your unit exam. It tends to be one of the trickiest ones. Okay, so let's go over this one carefully.
How do you know the difference if it's like slow, medium, or
That's what I'm going to explain with this question. Okay, so my before picture is this one. I have a crest that is approaching the boundary between medium 1 and medium 2. Okay? Now, a little while later, I have an inverted pulse traveling backwards in the first medium. And I have a very small, shorter pulse traveling forwards in the second medium. Okay? And it looks to me like it's also traveled a little further than this one. Okay? But that part of it I don't have to worry about so much. Okay? I need to determine whether the second medium is more or less dense, or faster or slower than the first medium. Okay? Now, one of the things that can tell me that is my reflected wave. Right? If my my transmitted wave didn't travel as far. Okay, so my reflective wave is inverted. Okay? If I get an inverted wave, that means it went into a more dense, which would also mean slower if it's a transverse wave, okay, a slower medium. Okay, that's one way I can tell. But then I can confirm it by doing this. My initial wave was this long. My initial wave was this long. My transmitted wave is a lot shorter. Would you agree? If it's shorter, it's traveling slower. Okay, because if the wavelength is going to decrease, that means the speed has to decrease. Okay, so that's a second way that I can tell. Okay, the last way I can tell, I don't know if they did a great job of it in this diagram, but this wave traveled that far. This wave, yeah, they didn't do a good job. It shouldn't have traveled that far. It should actually be like here. If they wanted to do a really good job. On the test, I do a really good job. Okay? I didn't do a good job. I just picked a good picture because you know how well I draw. Okay? So that wave there doesn't travel as far. Okay? Because these two waves, this reflected wave and this transmitted wave, have they had the same amount of time to travel? Okay, this one didn't go as far. Okay? It's smaller. Amplitude is smaller because some of the wave energy is in the reflected wave, so it's got less energy. Okay? And it's shorter. Its wavelength is shorter. Okay? That means, compared to this one, that it must also be going slower. Right? So there's three ways from a diagram like that I can tell whether the next medium is more dense or less dense than the first. Okay? Making sense there? That's wave behavior at a boundary really in a nutshell. Okay? We have to be able to do a question like that so that you can prove to me I understand that speed and wavelength change when a wave enters a new medium. I know that reflected waves have these properties when it's more dense and this property when they're less dense. Okay? That kind of stuff. Okay?
So are we able to say it goes from less dense to more dense instead of fast?
Yes, either way would be fine. Now, if it's a multiple choice question, you might have to, it might only give slower or faster. Okay, another waves traveling across a boundary. So we've got this spring, and then this, as they put it, light thread. And then they indicate that that means it's less dense than the spring. Okay, so we're going from a more dense medium to a less dense medium at the boundary of A. Okay, so first up, when the wave reaches A, what's going to happen? Some will be transmitted, some will be reflected. That's the answer basically all the time when it goes from one medium to another. Okay, now, the wave that travels into B, okay, is it going to be upright or inverted, the wave that is transmitted? Upright. Transmitted waves are always upright. Transmitted waves always look like the incident wave. Okay? The reflected wave is going to be what?
Upside.
It's going into a less dense medium. It's going into a faster medium. The reflection will be upright. Okay? You get an inverted reflection if it's going into a more dense medium. That's one of the ways we can tell. Okay? If it's traveling from more dense to less dense, I get an upright reflection. If I go from less dense to more dense, I get an inverted reflection. It's one of the ways you can tell and answer that question. Okay, so you have to know that. It's just something you have to memorize. Okay, that if a wave goes from a less dense medium to a more dense medium, there's an inverted reflection. Okay, if it goes from more dense to less dense, where it's going to travel faster, you get a very small upright reflection. Okay, reason being, less energy is reflected from an easy boundary. Okay, more energy is reflected from a difficult boundary. All right, so I get an upright wave traveling towards B, I get an inverted wave traveling back in the spring. When that upright wave gets to B, what's going to happen? It's going to reflect, yeah, all of it, because it's a fixed end. Okay, it's an infinitely dense medium into which the wave cannot travel. All right, so if that happens, it reflects, and it reflects inverted. Okay, notice I used upright, because people stop paying attention when I use the other word. Okay. All right. A spring runs across the floor of a room and out the door. Okay? A pulse is sent along the spring. A little while later, an inverted pulse returns. Is the spring attached to a wall, which would be a fixed end, or is it lying loose on the floor? Which do you think? It's attached to the wall. If it's lying loose on the floor, the waves are traveling from the dense spring into air, okay, which is less dense. And so I would get an upright, very small upright pulse returning. Okay? But I got an inverted pulse. That means it had to hit something more dense than itself. Okay? And one of the options was attached to a wall. Well, that's more dense than the spring, so I would get an inverted pulse returning. Okay? Okay, if I want to increase the wavelength of waves on a rope or a spring, okay, should I shake it at a higher or lower frequency? Which would make longer waves? A higher frequency or a lower frequency? Can someone be my fixed end? Hey, Ben? Right, just, I would hold it.
Don't get too crazy.
That.
Okay.
Okay, so if I shake this at a high frequency, okay, that's what my waves look like. Okay, if I shake it at a lower frequency, are my waves longer? Okay, so if I want to increase the wavelength, I want to shake it at a lower frequency. I mean, think about it. But if I make it at a higher frequency, am I making more waves in the same amount of time? That means they have to be shorter. Okay? I complete that oscillation a lot faster if I'm shaking it at a high frequency. That's going to make short waves. I'm going to need you again, because now you have experience in this job. And I like to hire people with experience.
I didn't want
Yeah.
them stretched out.
Oh, because we used to use these for a lab and people mistreated them. Still works fine for what we're doing. Okay, that one makes sense then? Okay, so another one of these pulses sent along this rope, this light rope, and it's attached to a heavy rope. So we're going from less dense to more dense, from fast to, okay. When the wave gets to A, some of it will be transmitted, and some will be reflected, and the reflection will be inverted because it's going into a more dense medium. Okay, the transmitted pulse is always upright. When it gets to B, what's going to happen?
Go back.
It's going to be reflected, and it's going to be reflected inverted because that's a fixed end. Okay, so easy, kind of common sense wave behavior at a boundary question. Okay, if I make this a multiple choice question on your exam, I expect 100% of you to get it right.
Does that never happen?
It always happens. That's why I expect it. Okay? What property of a wave, once it's produced, can never change? Frequency. Never, ever. Okay? I can change the frequency of other waves by changing the source and making new waves with a different frequency. But once a wave is traveling, its frequency cannot change. Okay? Absolutely cannot change. All right. This is just like the one I said would be on your exam. Okay? I draw two overlapping waves on a grid, and I ask you, is this constructive interference or destructive interference? And I ask you, draw the resulting waveform. Okay, so these waves are overlapping. Are they in phase or out of phase? They're in phase. When one is up, the other is down. Okay, so what kind of interference are we looking at? Constructive. Okay, so in constructive or any type of interference, the way I figure out the amplitude is to do what with the two waves? Add them together. All right, got 2 and 4, so I'm going to positive 6 up here, negative 6 down here, positive 6 up here, negative 6 here, positive 6, and all I'm going to do is connect the dots. Okay, I may not be right on for all the other points on this wave. That's okay, as long as I've got the crests of the waves and the troughs of the waves at the right amplitude, you're good. Okay, I kind of did a sloppy job here because I went too fast, but okay, that's exactly what you're going to be asked to do on your exam. Okay, is that a gimme question? I think we covered that. That's a gimme question. Okay. All right, in this diagram, okay, it's asking you what kind of interference is happening at specified points, because these waves are not in phase. Okay? They are in phase sometimes, but they're out of phase at other times. The result, if I asked you to draw the resulting waveform of this, you would probably go crazy. Okay? Because this would be very, very difficult to draw the resulting waveform. Okay? Because it would be a jumbled mess. Okay? So, at point G, so that's right here, is that constructive or destructive? Constructive. The amplitude is going to be greater there because both the waves are positive. Okay? At point I, what would we have? Destructive. Okay? I'm not saying you could draw a waveform here, but one is up, the other is down. That's destructive. Okay? Page 236.
Our game got canceled.
I kind of figured that. All right. Constructive or destructive? Destructive. One is up, the other is down. Okay? And O is the other one. Constructive or destructive? Destructive. One is up, the other is down. Okay? Is linear superposition and interference fairly straightforward? Okay? At that level, certainly it is. The thing we're going to talk about today, okay, which is standing wave patterns, combines wave behavior with interference. Okay? The two things are going to go together. Okay, how many people got a chance to do this one? The two-speaker question. All right, I'm going to give you 5-10 minutes, okay, to give this one a try. All right, I'll draw it. Okay, that might help you do it a little quicker.
She's so happy we don't ever do it. She's dying. I have so much to study. And we meet tomorrow too.
Yeah, it's gonna be colder tomorrow.
And we have a tournament in Rutgers. No, it's canceled. Really?
Well, on the weekends, it's gonna, like, the buses probably won't run on Friday.
Do you think school's happening tomorrow?
Oh, school's happening. School happens no matter what.
I
The buses
I
don't.
only had like 8 people in my first week this
Wait,
week.
then do you practice this week?
So, I'm not showing up for study tomorrow. You're the math.
I didn't know that.
You didn't know that?
I don't think my car
When the
will
bells
start.
first rang, it was me, Juliana, and Dick.
Yeah, so now we don't have a tournament.
I'm all the way from
The wavelength. So you do these two. Subtract it to get the difference.
Yeah. Standing here, speaker there, speaker there. A wavelength is so you take this number and divide by miles. That'll give you like if it subtracts those two numbers, also no, so if it's whole number, 3, 4, 5, it's loud. If it's 0.5, anything 0.5.
What did you get? Did you get she he can or can't hear? Is that hero?
Okay, we're ready to go over that one?
Yes.
Okay, because the guarantee, one like this is on your exam. I think I told you that the
On
other
the
day.
exam and the test.
The exam and the test are the same thing.
The final.
Oh, yeah, probably. Okay, so if we're looking at this one. Oh, I was recording the whole time. Nice, okay. So what we have to do on this one here, okay, is we have to first determine how far it is from the second source, speaker, to the observer, which I made an X because I tried to draw a stick person in the last class and it didn't work out very well. Okay, so I got to find the length of that line. So in order to do that, I just got to do Pythagorean theorem here. So that'll be square root of 6.42 squared plus 6.8 squared. Okay, and that comes out to 9.35 meters. Okay, so now I know that distance. Now, what determines whether the observer hears a loud sound or a quiet sound is whether the waves meet at the same point in the cycle. Okay, what determines that is how many wavelengths are there between the speaker and the observer from each speaker. Okay, if that difference is a whole number, are they arriving in phase? They are. If that number is something 0.5, are they arriving in phase? No, they're arriving completely out of phase. And that would be destructive interference and be a quiet sound. Okay, so if I'm going to determine the number of wavelengths on each side, I need to know the wavelength. Can I get that with these two numbers?
Yeah.
Okay, so wavelength equals V over F. Okay, so that'll be 340 divided by 400. I think it comes out to 0.85, yeah?
Yep.
Okay, so now I know the wavelength is 0.85 meters. So if I want to determine how many wavelengths there are on this side, I divide the length of the side by the length of one wave.
It's 0.085.
No, it's not. Okay? 340 divided by 400.
Look.
Okay, so we've got to divide this side here, the hypotenuse, 3.35 or 9.35, divided by 0.85. Okay, and we got 11 wavelengths. Okay, so there are 11 full cycles on that side. Okay, we've got to do the same thing over here. 6.8 meters divided by 0.85 meters. That'll tell me how many waves. Okay, so 6.8 divided by 0.85, right, gives me exactly 8 wavelengths. Okay, so 11 wavelengths minus 8 wavelengths gives me 3 wavelengths. Full whole number. Right? Loud or quiet? Loud. Okay? If it's a full or it's a whole number, then they're arriving in phase, crest to crest and trough to trough, because they travel and get to the same point in the wave when they get there. Okay? If this side was 11.5 wavelengths, then we would have a difference of 3.5, and we would have a quiet sound because one would arrive as a trough because it travels half a wavelength further. Okay? All right. Questions on that one? Okay, now just so you know, on a test, this is like a 6-mark question. You don't get 6 marks if you just guess quiet and it's right. Okay?
You don't.
This is one of the few situations where work matters. You have to prove something worth 6 marks.
Wait, what if
Okay.
you do your work wrong, but you still get the right answer?
Then you'll lose marks for the work.
What?
I'll give you all the marks for the work right, but then at the end, you just guessed. Yeah? I mean, if you do the work right, you will get the right
But
loud
what
or
if you
quiet.
do it wrong, but still get technically like the right loud or quiet?
I don't see how that could happen. Okay. It's a good hypothetical scenario. I've just never encountered it in 25 years of teaching.
What if you just write the number and don't show the word?
Then you don't get, that's what I just said. If you just write loud,
No, but like the number.
I still need to see your work.
Oh.
Yeah. Okay? You should always show your work. Show your work. It's super important. I know. I'm just saying that for the benefit of everybody. Okay. Questions there? All right, so we've got 2 examples of that now in your notes. Okay, that one and the one we did on the day we taught interference. I'm sure you go over those prior to the test. I think I put another one on the unit exam review that you can try as well.
Will it ever ask for something other than loud or quiet?
No. It will be just like this. I wouldn't give you, they hear a loud sound, so how far are they from the first speaker? Not that that would be all that hard to do, but I just wouldn't do it. Okay, moving on to standing waves now. Right, so standing waves are kind of the result of all the stuff we've been talking about. Wave behavior, reflection, okay, also interference, okay, all of that stuff is what produces standing waves, which probably have the worst name ever for something in physics. Because standing implies you're doing what? Not moving, okay? The waves that produce standing wave patterns are moving. What appears to sit still is the pattern they make. And even that doesn't really sit still. If you're going fast enough, it appears to sit still. Okay? But standing waves are not standing. Don't let that, it's a misnomer. Okay? They are waves traveling back and forth on a medium. Okay? And they are interfering with each other in that medium and they create a pattern. Okay? That pattern is fixed. Okay? But it is the result of interference and it is moving up and down the entire time. So, Ben, I'm going to need my fixed end again. Thank you. So, standing waves can only be produced at certain frequencies. Okay? That frequency is dependent on the properties of the wave. Okay? How tight the spring is. Okay? Things like that. Everybody with me so far? Okay, so the simplest standing wave pattern that I can make on this spring is this one. Okay? That is the simplest standing wave pattern that can form. It's always going up and down in the middle, and at the ends it's doing what?
No.
Not moving. Okay? I mean, I'm the source, but right in front of my hand is essentially an area where it's not moving. Now, look at how much the middle is moving versus how much my hand that's creating the waves is moving. My hand's moving up and down maybe 5 centimeters. Okay? The amplitude in the middle is probably closer to a meter. Okay, from equilibrium. How's that happening? Where's the energy for that coming from? What can cause the amplitude to get bigger? We just talked about it. What can cause the amplitude to increase when waves are occupying this constructive interference? Okay, because what we have going on here is a whole bunch of waves that are identical in wavelength, speed, and frequency, occupying the same space at the same time. I'm making little tiny waves. Okay, they're going across the spring, hitting Ben's hand. Okay, and because Ben is infinitely dense, okay, he's a nice guy, okay, but he's an infinitely dense medium over there. He's a fixed end. Okay, the waves are bouncing off of his hand and coming back. They're meeting the next wave that I produce. Okay, and I keep producing. I keep putting more and more wave energy in the medium. Okay, and while some of it, peters out due to friction and whatever, okay, more and more energy is constantly being put in here, and that energy is always interfering constructively in the middle.
Wait, so what's the answer to your question?
I don't know, so long ago they asked the question, I don't even remember. Oh, what can cause the amplitude to be greater was my question. And the answer was constructive interference. Okay? Constructive interference is occurring in the middle. What kind of interference is occurring right at Ben's hand? Destructive. Okay? Here's why. Think back to our wave behavior at a fixed end. When a wave encounters a fixed end, it always reflects, but it always reflects inverted, which means the wave is always producing its exact opposite at the point of reflection. So it's always going to produce complete destructive interference at that point. Okay? That sort of makes sense? Okay, so let's say I'm shaking this at a frequency of about, I don't know, let's say it's 1 hertz. Okay? So I'm making 1 oscillation per second. How fast am I shaking it now?
Faster.
How much faster? Look at the structure. 2 times faster. Okay? This is the second standing wave pattern that can form on the spring. It's called the second harmonic. The one I produced originally is called the fundamental frequency, or the first harmonic. It's the first frequency that would produce a standing wave. This is the second frequency. All frequencies that can produce a standing wave are called harmonics, and they are always multiples of the first. So this is the second harmonic, or F2. It is 2 times greater than the fundamental. Okay? If I shake this 3 times faster, what's the wave going to look like?
3 humps.
It'll have three antinodes. We're going to use the correct terminology because humps is insensitive to chemicals. Okay? Or something like that. Okay? So now I got 3 hertz. Okay? And that gives me, well, it starts to twist. It's hard to keep it straight when you start going faster. I gotta wait for it to peter out here. It just becomes a mess. Okay? So at 3 hertz, I get 3 antinodes. Okay? It's the next fundamental. Okay? If I shake it faster, I can get 4. My record is 5, but I can feel my back getting sore already, so I'm going to stop at 3. Okay? You guys get the idea, though? Okay, so standing waves, which is what we just produced there, result from repeating patterns of interference. Reflected waves and produced waves from the source are traveling back and forth in the medium, okay? And because they have the same speed, wavelength, and frequency, okay, they are going to produce a pattern of interference. Okay? How those patterns are formed? Well, you've got to have the right frequency. You've got to have the right speed and wavelength. Everything's got to match. Okay? And then we're going to learn the names of the proper names of the areas of destructive and constructive interference. So an area of constructive interference is called an antinode, which means the destructive interference are called nodes. Antinode and node. Physicists aren't very creative, apparently. Okay, so that's the proper terminology. Okay. All right, so this is what I showed you, but it's freeze framed. Okay, these are the 3 standing wave patterns that I produced there a minute ago. Okay, so this one is F1. Okay, it is our fundamental frequency. You don't have to write this down because it's on the next slide too. Okay, fundamental frequency. And then this is F2. It's the second harmonic. This is F3. It's the third harmonic. If this is 1 hertz, this is 2 hertz. This is 3 hertz. If this is 10 hertz, this is 20. This is 30. It's always a multiple of the next. Okay? This is how all musical instruments work. Okay? So musical instruments work by producing standing waves, either on a string, so it's a string instrument, okay, or using a column of air that's vibrating. Okay? So if you have a saxophone, a clarinet, any of the ones that have a reed, okay, the reed is the source of the vibration. You blow across it, the reed vibrates, okay, and then what you do is you push the buttons. I don't know what they're actually called. They're actually called buttons.
What would that tuba or trumpet be then?
Same thing. It's an air column. Okay? Any brass, all the brass is an open air column. Okay? So when you push the buttons, what you're doing is changing the length of the tube of air that can vibrate. And by doing that, you change the wavelength of the waves. On a string instrument, if you're playing like a guitar, for example, okay, where you pinch the string against the bridge determines the wavelength of the sound that string produces. Okay? If it's really short, it produces a high frequency wave. If you don't pinch it at all, you get the fundamental frequency of that string. Okay, you get the full length of it, and you get a low frequency sound. Right? A piano works the same way. I don't know if anyone's ever seen the guts of a piano. Okay, but if you look at like a grand piano, any piano, okay, but a grand piano has this shape. Okay, and that's because in it are strings of different lengths. Okay, and as you go from left to right on a piano, I don't know much about music, but I know how the piano works. Okay, you produce higher frequency of sound with the keys on the right. Okay, because the keys on the right are attached to the shortest strings. Okay, and here's the other interesting thing about piano. Okay, is if this is playing a C note, the next C on the piano, the string is half as long as that one, because it's going to produce a frequency twice as high. It's the next fundamental of that note. Okay, that's how you get different musical octaves. Okay, you get octaves are the next harmonic of that note. Okay, does that sort of make sense? So the same would be true on a guitar. Okay, if I want to play the next octave of a note that string produces, I change the length of the string. Okay, now for a piano, you just have lots of strings. Okay, and if you want to tune a piano, you just change the tension in those springs. If I change the tension, I change the speed at which the waves travel, okay? Which is going to change their frequency, and they're going to sound different. You really notice that if you're tuning a string instrument, like a guitar. Okay? So if you strum it and then you turn the knob, okay, and you tighten or loosen the string, you can hear the frequency change when you do that. Okay? And that's because you're changing the speed at which the wave can travel, and as a result, the frequency at which it can vibrate. Okay, making some sense? Now, a guitar only has, well, usually 6 strings. Okay, so in order to produce different notes, you have to make those strings shorter or longer. Okay, whereas in a piano, you just hit a different key. Okay, making sense?
How do the pedestals work on the piano then?
That one I couldn't tell you. It does something to the reverberation of the sound, I believe. Okay, so it opens up a baffle or something in the piano and changes how the not so much the frequency, more how much it reverberates or how long the notes. Because I think one of the pedals actually squashes puts a pad down on the strings to stop them vibrating. Yeah, something like that. Okay. Yeah. Everybody okay with that one? All right, so the names of the different spots. Okay, as we said, the antinodes are the positions of constructive interference, and the nodes, which they do not identify all of them. Okay, these two, yes, are obviously nodes, but there's a node here and a node here as well. Okay, nodes are places that do not vibrate at all because they experience complete destructive interference. Okay, and then the opposite is true for our antinodes. Okay? Antinodes are places where maximum vibration occurs because they are areas where constructive interference is occurring. Right? Now, just as I said before, okay, we named these different waveforms, right? The first one we get is called our first harmonic slash our fundamental frequency. Okay? Now, if this distance here is 1 meter, what's the wavelength? 2 meters. How much of the wave is on that right now? Just half, right? Like 1 full wave cycle has to go out to here, right? To get the full wave cycle. So 1 meter is half the wavelength at the fundamental frequency. So when anything is vibrating at its fundamental frequency, okay, the wavelength is twice the length of the oscillation. Right? That is all you ever get in a string instrument. You never get a string instrument that gets like all wavy. Okay? It'll only ever resonate at its fundamental frequency. All right? Now, for the second harmonic, and by the way, if you have a diagram and it talks about overtones, we don't talk about those because they're confusing because the numbers don't match. Okay? So, for the second harmonic, we get a full wavelength on the string this time. Okay, so if that's 1 meter, the wavelength is 1 meter. Okay, the frequency required to produce that waveform is twice the original frequency. Okay, and so on and so on. This would be the third harmonic would be this one. Okay, it would be 3 times. Okay, the fourth harmonic would look like this. You'd have 2 complete wavelengths on the string, okay, and it would have to be at 4 times the fundamental frequency. Okay.
So to find the wavelength of the one that has 3, you just have to like minus a third.
Or just divide it by 1.5. You have 1.5 wavelengths on there. Yeah? Does that make sense? Like this is one wavelength and that's another half a wavelength. Okay. Okay, so that's what sorry, I have another kind of a repeat slide here, but it's basically the same thing. Okay, remember that those are the harmonics, okay? They're factors of the first. That's how we create the different musical octaves. Okay, so standing wave patterns arise because we have identical waves traveling back and forth in a medium. For musical instruments, that is ideal. This is the only way we would produce sound and be able to amplify it acoustically. Okay? It is not ideal if it happens in a structure, like a building or a bridge. If you recall, remember I showed you that short video clip of the bridge that was doing this? Okay? That's a real bridge. It's the Tacoma Narrows Bridge. It was built in the 40s. I'm going to watch that. We're going to watch it today. Okay? So the thing about the Tacoma Narrows Bridge was not that it was poorly designed. Okay? It was actually designed by Leon Marseille, who at the time was the guy to design suspension bridges. He had spent his entire life designing suspension bridges all over the world. Okay? He was the master of building suspension bridges. This bridge was a technological leap. It was very long compared to its width, which presents problems for creating and keeping tension in the bridge. Okay? Now, again, this was a guy whose whole life was about suspension bridges. He knew what he was doing in the 40s. Okay? What happened was something that had never happened before. And in fact, it took them 50 years to figure out why it happened. They were able to prevent it from happening again very easily. But figuring out why it happened took 50 years. Okay? So, what happened was there was a sustained wind of almost a constant velocity for several days, which is unusual. Very rarely do you get a constant velocity of wind for a long period of time. Okay? But because of the way the Tacoma Narrows goes, it's basically a long, narrow chute, okay, or canyon. Right? So wind only has one way to go, and it's right down the chute, something they may have overlooked a little bit. Okay? But I don't think they ever suspected they'd get a sustained wind through that chute for several days. Okay? And so what happened is as the wind blew across the bridge, it would start the bridge to oscillate. And the bridge was designed for that. Okay? In fact, people would come from miles around to watch it do this, okay, and drive across it. It was fine if the bridge was just bouncing up and down. The bridge was totally designed to take that.
What was it made of?
Steel. This was a great bridge. concrete and steel. Okay? But it was designed to be flexible enough that it could oscillate up and down and basically take these waves that would be produced by wind. Like this guy knew what he was doing. His whole life was building bridges. Okay? But the problem with the sustained wind was it was a constant input of energy to the bridge. It kept pushing on the same side. Okay? And what was worse about that was when the bridge started to oscillate, that was fine. It could take that. It got to the point where they stopped letting traffic across because it got a little bit extreme. And then all of a sudden, it started to twist. Okay? Because this sustained wind was blowing across the bridge and pushing up on one side, and then the bridge would slow that wind down and it would spiral under the other side. So one side's getting pushed up by the bridge, but it's creating a vacuum on the other side that's sucking the other side down. Okay? And that was never accounted for. So the whole bridge started doing this, and it was never designed to have two antinodes. And it was designed to do this. That was okay. Up and down, have one antinode, totally cool. But when you suddenly get a node in the middle, you're in trouble. No bridge is designed to twist, okay, in the middle. Right? It would have to be made out of rubber, okay, for something like that to work. And it was made out of steel and concrete. Okay.